Welcome to the Explainer. Today, we're going to take absolute unyielding chaos and transform it into perfect order. Think of it as combining motion and modern art to visually organize things. We're tackling one of the most elegant concepts in computer science, but, we're going to do it in a way that feels totally intuitive. So picture this. You're standing in front of a completely disorganized line of people, just a messy, chaotic queue. You need to start them by height, from shortest to tallest, and you need to do it fast. How would you organize this disorganized dataset without getting totally overwhelmed? If you try to compare every single person to every other person, you'll literally be there all day. You need a way better strategy. Well, that better strategy brings us exactly to the formal definition from our source material. It's called quicksort. It is a highly efficient, divide-and-conquer sorting algorithm. It organizes elements by selecting a pivot and partitioning the array around it. Okay. That's the technical definition for sure. But what does it actually mean for our messy line of people? Section 1. The queue line analogy. Finding order in chaos. Okay, let's dive into this. Instead of looking at that whole daunting line all at once, we use a brilliantly simple trick. Here is the absolute core mechanism. You walk up to the line, close your eyes, and just pick one person at random. Doesn't matter who. Then you shout two simple instructions. If you're shorter than this person, move to their left. If you're taller, move to their right. Instantly, without even fully sorting the whole line, you've created two smaller, much more manageable groups. Believe it or not, you literally just executed the official steps of quicksort. Let's map our analogy right to the algorithm's actual logic. Step 1, choose pivot. That random person you picked, that is your pivot. Step 2, partition. That's the physical splitting action of moving shorter people left and taller people right. Step 3 is recursive sorting, and step 4 is repeat. And we're going to hit those last two right now. And this brilliantly illustrates the result of that partition phase. On the left of your pivot, you have a group of all smaller elements. On the right, all larger elements. Now, notice that the two separate groups aren't fully sorted internally yet, but the pivot, that one person you originally chose, is exactly where they belong in the final sorted line. They never have to move again. It's locked in. Section 2, the magic of recursion, dividing the problem. So we have our pivot locked in place, right? But we still have two messy groups on either side. How do we fix them? Recursion. We take the exact same logic we just used and apply it to the new, smaller lines. We zoom in on that smaller line of shorter people on the left. Boom! We pick a new random person in that group as a new pivot. Shorter to their left, taller to their right. It happens in an absolute instant. And at the exact same time, we're doing this to the right subarray. We look at the group of taller people. Boom! Pick a pivot. Shorter left, taller right. We are rapidly fracturing the problem into tinier and tinier pieces. The sheer speed of this algorithm comes from this relentless, simultaneous division. And we just repeat this rapid-fire pacing until we hit our base case. Basically, repeating until subarrays contain 1 or 0 elements. Think about our line again. If you keep dividing groups, eventually you're going to end up with a group of just one person. And a group of one person, well, that's automatically sorted. Once every tiny subgroup is down to 1 or 0 people, the entire massive queue is perfectly flawlessly ordered. Section 3, Real-World Impact. Why systems love it. Now, what's really interesting here is how this theoretical magic translates into actual computing power. Why do operating systems and heavy-duty software absolutely love quicksort? Well, it's incredibly powerful for large datasets because of its strong average case performance. But the real kicker here is the in-memory sorting. Quicksort has what we call in-place sorting capability. It doesn't need to create massive duplicates of your data to sort it. It just swaps things around right where they are. This makes it wildly efficient for fast general sorting and dealing with random access structures, like vectors, that need to fit snugly right into your computer's active memory. Because of that incredible efficiency, its heavy-hitting applications are, well, literally everywhere. System libraries, tons of programming languages use optimized variants of quicksort right out of the box. It's a massive staple in competitive programming because of its speed and simplicity. Massive database systems use this internal logic to sort through millions of records, and heavy data processing pipelines rely on it to organize huge collections quickly. The exact logic you just learned with our queue of people is literally running inside your computer right now. Section 4. Common mistakes. The pitfalls. But let's shift gears for a second. What happens if you execute this brilliantly fast algorithm poorly? Here is the absolute biggest trap. A bad pivot choice.
Imagine you're sorting that line of people, but instead of picking a random person, you always happen to pick the absolute tallest person or the absolute shortest. Everyone would move to one side, and you haven't actually divided the problem at all. In algorithmic terms, this degrades your blazing fast speed into O of n squared performance, meaning the time it takes to sort grows exponentially with every single person added. It becomes painfully slow, acting way more like a clunky beginner's sorting method. No way do we want that. And there are a few other technical dangers too. If you get highly unbalanced partitions over and over, you can actually trigger a Stack Overflow, essentially running out of computer memory because the program gets way too deep into dividing. Or if you forget your base case, that absolutely crucial stopping condition of 1 or 0 elements, the program will just run infinitely, desperately trying to divide a single person in half. Finally, incorrect partition logic, like mishandling the actual swapping of elements, will just leave you with a broken, unsorted mess. So, the absolutely crucial point to remember is this. Quicksort organizes elements by selecting a pivot and partitioning the array around it. If you respect the pivot and divide the problem cleanly, you unlock immense speed. You've just walked through and successfully mastered the logic of one of the most famous divide-and-conquer algorithms in the world. Which leaves us with this final provocative thought. If a few lines of code can organize absolute chaos this efficiently just by dividing a big problem into manageable pieces, what else can we sort out? Think about how this perfectly mirrors basic human problem solving. Next time you're overwhelmed by a chaotic situation, remember quicksort. Pick a pivot, divide the problem, and sort it out step by step. Thanks for joining me for this explainer, and keep looking for that hidden structure inside the chaos.